Earth's breathable blanket, the atmosphere. Our planet Earth is enveloped by a delicate, life-sustaining layer known as the atmosphere. Imagine it as a giant bubble, holding in the air we breathe and protecting us from the harsh vacuum of space. This gaseous shield consists of different layers, each with its unique characteristics. The layer we experience daily is called the troposphere. This is where weather, as we know it, unfolds. Clouds form here, rain falls, and winds howl. The troposphere is a dynamic and ever-changing part of our world. Above the troposphere lies the stratosphere, home to the ozone layer that shields us from harmful ultraviolet radiation. Beyond the stratosphere are the mesosphere, thermosphere, and exosphere, each with its own fascinating properties, gradually fading into the vastness of space. It is within the troposphere, however, that the captivating drama of weather patterns plays out, influenced by a delicate balance of atmospheric elements. Weather's building blocks: temperature, pressure, humidity, and wind. Weather, in its essence, is the state of the atmosphere at a given time and location. It is the result of the interplay between four key elements: temperature, air pressure, humidity, and wind. Temperature, a measure of heat energy, dictates how much moisture the air can hold. Warmer air can hold more moisture than colder air. This difference in moisture capacity drives many weather phenomena. Air pressure, the weight of the atmosphere pressing down on the Earth's surface, varies across the globe. High-pressure areas generally experience calm and clear weather, while low-pressure areas are associated with storms and precipitation. Humidity refers to the amount of water vapor present in the air. High humidity combined with warm temperatures can make us feel muggy and uncomfortable. It is also a key ingredient for cloud formation and precipitation. Wind, the movement of air from areas of high pressure to areas of low pressure, plays a crucial role in distributing heat and moisture around the globe. Wind speed and direction influence the movement of weather systems and the severity of storms. The symphony of weather: how atmospheric elements collide. Weather patterns emerge from the complex interplay of temperature, pressure, humidity, and wind. These elements don't exist in isolation but constantly interact, shaping the atmospheric tapestry that dictates our daily weather experience. The sun's uneven heating of the Earth's surface creates temperature differences, which in turn drive air pressure variations. Warm air rises, creating areas of low pressure, while cooler air sinks, leading to high pressure zones. This constant movement of air masses is the engine of weather patterns. Humidity adds another layer of complexity. As warm, moist air rises, it cools, causing the water vapor to condense into clouds. Depending on the temperature and the amount of moisture present, these clouds can produce rain, snow, sleet, or hail. Wind acts as the conductor, guiding these weather systems across the globe. Jet streams, high-altitude rivers of wind, play a crucial role in steering weather patterns from west to east in many parts of the world. The interplay of these elements is a delicate balance, constantly shifting and evolving, creating the dynamic and ever-changing nature of weather. The eyes of the storm: real-time observation in weather forecasting. To predict the weather, we need to understand the present state of the atmosphere. This is where real-time observation comes into play. A global network of observation tools constantly monitors the atmosphere, gathering crucial data on temperature, pressure, humidity, wind speed, and direction. Weather balloons, launched twice daily from numerous locations worldwide, ascend through the atmosphere, carrying instruments that measure atmospheric conditions at various altitudes. These balloons provide a vertical profile of the atmosphere, crucial for understanding weather patterns. Ground-based weather stations, equipped with an array of sensors, provide continuous measurements of temperature, pressure, humidity, wind speed and direction, precipitation, and other weather variables. These stations form the backbone of our weather observation network. Weather radar systems emit radio waves that bounce off precipitation particles, providing information about their location, intensity, and movement. Doppler radar, a more advanced type, can also detect wind speed and direction within storms, aiding in severe weather forecasting. Section 5. Predicting the skies: supercomputers as weather oracles. Weather forecasting relies heavily on the power of supercomputers. These computational behemoths process vast amounts of data from weather observation networks worldwide, using complex mathematical models to simulate atmospheric processes and predict future weather conditions. Supercomputers are essential because the atmosphere is a chaotic system. Small changes in initial conditions can lead to drastically different outcomes over time. This is known as the butterfly effect, where the proverbial flap of a butterfly's wings in one part of the world could theoretically influence the formation of a hurricane thousands of miles away. To account for this complexity, weather forecasting models divide the Earth's atmosphere into a three-dimensional grid. Each grid point represents a specific location and altitude. The supercomputer uses observations and mathematical equations to calculate how weather variables like temperature, pressure, humidity, and wind speed at each grid point will change over time. By running these calculations for multiple grid points across the globe and over different time periods, supercomputers generate weather forecasts ranging from hours to weeks in advance. Section 6, From Data Deluge to Digital Skies. Simulation and Weather Forecasting. Weather simulations, powered by supercomputers, are essentially virtual representations of the Earth's atmosphere. These simulations take into account the complex interactions between atmospheric variables, allowing meteorologists to predict how weather patterns might evolve. Imagine a digital globe, meticulously detailed with mountains, oceans, forests, and cities. This virtual Earth is then overlaid with a three-dimensional grid, each grid point representing a specific location and altitude in the atmosphere. The supercomputer ingests a constant stream of data from weather balloons, ground stations, satellites, and other observation tools. This real-time data provides the initial conditions for the simulation. Using sophisticated mathematical equations that describe the physics of the atmosphere, the supercomputer calculates how the conditions at each grid point will change over time. These calculations are incredibly complex, taking into account factors like solar radiation, heat exchange, cloud formation, precipitation processes, and the Coriolis effect caused by Earth's rotation. As the simulation progresses, it generates a virtual forecast depicting how temperature, pressure, humidity, wind patterns, and precipitation might evolve over the forecast period. Section 7. The Sharpening Forecast. How Technology Improves Predictions. Weather forecasting has come a long way from rudimentary observations. Advances in computing power, observation systems, and data assimilation have dramatically improved forecast accuracy. The exponential growth in computing power allows us to run more complex weather models. Today's supercomputers perform quadrillions of calculations per second, simulating weather with precision. Our ability to observe the atmosphere has also improved dramatically. Satellites provide a global view, capturing high-resolution images and tracking storms. Advanced radar systems offer detailed information about precipitation and wind patterns. Improved data assimilation techniques integrate data from various sources. These techniques blend observations into models, providing a more accurate picture of the atmosphere. Section 8. AI Weather Wizards. The Future of Forecasting. Artificial intelligence, particularly machine learning, is poised to revolutionize weather forecasting even further. Machine learning algorithms excel at identifying patterns and relationships in vast datasets, making them ideal for analyzing the complex and often chaotic nature of weather data. AI can sift through massive amounts of historical weather data, identifying subtle patterns and correlations that might escape even the most experienced meteorologists. This allows AI to learn from past events and improve its ability to predict future weather patterns. Moreover, AI can analyze data from various sources simultaneously, including satellites, radar, weather balloons, and social media feeds. By integrating these diverse data streams, AI can provide a more comprehensive and nuanced understanding of developing weather events. For example, AI algorithms can analyze satellite images to identify the early stages of hurricane formation, track the movement of wildfire smoke plumes, or predict the likelihood of flash floods based on rainfall patterns and soil moisture levels. Section 9. The Unending Quest. The Continuous Evolution of Weather Forecasting. Weather forecasting is a constantly evolving science. Despite advancements, challenges remain. The atmosphere is chaotic, and even sophisticated models have limitations. Ongoing research aims to improve model accuracy and develop new technologies. Ensemble forecasting assesses uncertainty by running multiple models. Comparing these runs provides a range of possible outcomes. Nowcasting offers highly localized, short-term predictions. It relies on real-time data from various sources. The future lies in collaboration to push prediction capabilities. If you like this content, please comment, like, and subscribe.